All right, so here we are at an example that brings an application of how we can apply rate of change as well as the derivative concept in the business field and in the field of business and economic studies. All right, so let's, as usual, let's spend some time reading the wording description of our example here. So before we get to the actual question, then what it says here is that according to the U.S. Bureau of Economic Analysis, U.S. total personal income from the time frame anywhere from 1960 to 2018. So this is more than, this time frame right here is a time interval for over 50 years. And the U.S. total personal income is notated by the I variable. And so again, let me finish reading my statement here, but U.S. total personal income from 1960 to 2018 can be modeled by the following function. So I of t equals 6.29 t squared minus 51.7 t plus 601, where t, so you can see that this is now I of t is a function. And it's a function of the variable, the main and the only variable t. And so here is a quick explanation of what the t variable is. So t is the number of years that passed 1960. Okay, and so now let's get started into question A. So question A is asking what is the average rate of change in total personal income I of t. Well, there is a little typo here, but it's supposed to be I of t from 1980 to 1990. And so, as the wording is describing quite obviously here, then this question is specifically looking for the average rate of change. And so that's making it consistent with the fact that in the question right here we are given a time interval from 1980 to 1990. All right, so because again, as I can quickly remind anyone that in the concept of average rate of change that we already discussed in the general discussion of understanding the rate of change, then average rate of change happens when we actually have a given interval of your main variable. So we do have, in other words, back in our problem here, we do have a starting value for our interval right here at 1980, and we have an ending of our interval at 1990. And that's what I meant by we're given a finite interval of values, and here in this case here, our interval of values here is the value for time. So we have an interval for time. And so before we get further, I just have to clarify that, and now allow me to start writing on the board here. But so recall that our variable t is the times past 1960. And so t is the time past 1960. And so that means when we're actually looking at our interval, the wording itself was saying that, see, let me briefly write down, we're looking at from 1980, okay, to 1990. But so this is not really our interval. I mean, it's the interval, but this is not the way how the interval is written. 1980 is 20 years, because that's how we define t. So 1980 is 20 years past 1960. So that means really our initial time here is t equals 20. So how do I know it's 20? Well, quickly, a simple math can answer that question. 1980 as our current time of spot right here, subtract 1960 right here. That's how I know that we are looking at 20 years past 1980. But hopefully no one needs to get that ridiculous explanation of mine. Okay, but so in that way, 1990 here means t equals 30 years. Okay, So in that way right here, precisely speaking, the question itself, now let's one more time have a look at the question itself right here, but the question in this way is looking for the average rate of change in, of course, total personal income, but in between the interval that's anywhere from t equals 20 to t equals 30. Okay? And so quickly back on my board, the real interval we're looking at here is, and the wording is saying from, so from 20 years after 1960 to 30 years after 1960 again. So that's the interval that we really are aiming at. Okay, so now with all that explanation ahead of time, let's really get started into it. And I am going to also spend a little time writing down our personal income function, because in the way how I see it, and I mean the example I'm bringing up here is not necessarily directly applicable to anyone's field, but think about there are people who are looking into a future working for the, who knows, the US Bureau of Economic Analysis. And so the way how I see that now is the personal income, the total personal income. It's not one personal income. It's like the total of all personal incomes in a year. And so that amount can be regarded as a quantity. So that quantity here has a variable I in this case. So now that's how we developed our function I of t as the function 6.29 t squared minus 51.7 t plus 601. Okay, and so the time now is, so that means here's our function. So average rate of change, as we have already studied throughout the general lecture, the general discussion lecture regarding rates, average, and I particularly made some distinguishment between average rate of change and instantaneous rate of change. This particular question in our problem A right here, in our question A, we're looking for average rate of change. So the way of doing that, so our goal is to find the average. AVG of mine stands for average. So average rate of change, okay, is famously final value. So our interval is anywhere from 20 to 30. Okay, and I apologize for writing it down so many times and keep erasing it and rewriting it. But so average rate of change is famously known for the final amount. So that means with this current modeling function, we're looking at I at 30. So I of 30, the total personal income in the US 30 years after 1960. That's what I call the final amount, minus the initial amount. So again, capital letter I stands for total US personal income. And so this is I-20, so initial amount. Final amount minus initial amount, or final function value minus initial function value, and divide that by the total change in time right here, the total change in our main variable of the function. So here we're looking at the change in the t variable, 30 minus 20. Okay, and so now that's the setting up for that. And so let's go ahead and do some calculation here, right here. I am quickly going to step away and do a calculation. Okay, but now allow me to quickly step away and do a quick calculation. All right, so here we are ready for the calculation. Now, so before I write down the calculation, now I have to clarify that this one part that was missed from the wording of the example. I mean, it was skipped. I apologize for that skipped information. But whichever the figure that comes out, that would come out from each of these value right here, whichever the outputs of the function here, meaning I at 30 or I of 20 right here, the value there is in billions. So if it's like if it comes out being a number being 65, that means 65 billions and all that. Okay, and so now my calculation shows I of 30 here is going to be 4711, but this means 4711, 4,711 billions. Okay, what we're talking about, we have a really large nation here, a really big, highly dense nation. So the figure here, even though in four figures are already, but it's already representing billions. Okay, and so now I at 20 here means we're going to subtract 2083, that according to what came out from my calculation. And so again, this number here is it's 2083 billions. Okay, and we are now dividing by 10 because 30 minus 20 is simply 10. So it's a rate, it's a fraction, it's a ratio between the change in total personal income over the change in time. And that's why, and I believe I've spent enough time talking about the concept of rate of change throughout our general discussion, the lecture like that. And so now it's just a straightforward calculation here that all right, so calculation of mine came out being, so in the numerator we are looking at 2,628, but this is again in billions and divided by 10 years. And so the math now can become a lot easier. That's going to be 262.8. So now here I'm looking at on average, and it's, by the way, it's a positive final calculated value right here. So it means on average in this time frame of 10 years apart, in this 10 years from 1980 to 1990, then we are looking at a getting more, an increment, an increase of total personal income by 262.8 billions. Okay, and so that's the value right there. And so that's the interpretation. So let me quickly swing by the other board and write the meaning of that. So this is only an interpretation. So on average, in a whole time frame of 10 years from 1980 to 1990, and on average from 1980 to 1990, okay, U.S. total personal income. Okay, and this, I like to use the word grew because it's a little friendly, but more formally it's increased in a much more formal math term. So we can say that that quantity grew or increased by 262. And see, again, connecting with what we've learned throughout the lecture, a positive rate of change means it's the value, the function I, the output of our function I value is growing, and that's how I know to use the word growing in the right place. So as you can think about as an impact of what I was saying just now, then in case your calculation came out being a negative value, that means it was the quantity decreased at that time frame, or shrunk. Okay, in here instead of growing, it could be shrinking. But here, back to our problem here, then it's 262.8 billions. Okay, large amount, and it makes perfect sense for our larger, heavily populated nation. Okay, and so that is the answer to part A. And really, as far as the answer, what I just wrote on the other board, which is a final interpretation, but really this is just the answer right here. Okay, and so now let's advance to part B of the example. All right, so now we're done with part A. Let's now look at part B. So the same function there and the same beginning description right there. And again, I apologize for having this typo that it's supposed to be the I of t instead of I of x as written here. Okay, and again, we're looking at the same exact modeling function in a time period from 1960 to 2018. And then again, t means the number of years past 1960. But now, the question here is looking for, in question of part B right here, of our current example. What is the instantaneous rate of change in total personal income in 2000? Okay, and so, and that's the information to be highlighted. And so, and right here, okay, so instantaneous rate of change of personal income, total personal income. So now again, connecting back to what I was explaining, hopefully detailed enough throughout our lecture for rate of change, then instantaneous rate of change is the kind of rate of change that happens only at a very slight, I mean as a math term, infinitesimally small instant. Okay, and so for that reason, now to make it easy for anyone viewing this video or any other videos where I talked about instantaneous rate of change is the kind of rate where you're, instead of having a full interval like this, nope, instantaneous rate of change, now instead of having a full interval, we are going to be looking for the rate that happens only at one instant. And so in this case, we're looking at 1 instant of time. So now I am going to start erasing the work for part A here. But retaining most of that structure, now we'll want to find the instantaneous rate of change in the year 2000. See, this is what I was saying earlier. This year 2000 right here is only one single instant of time. Okay, and so we don't have instead of having beginning and final of the interval, we only have one single point of time, of one single point value for our variable, and we are expected to find a rate of change that happens only at that instant. And that's what instantaneous rate of change is all about. Because think about it, really, in 2001, it could be just a year later at that different instance, it's going to be a different rate. Okay, it's going to be a different, it could be growing or shrinking, but it's completely a different rate, Okay, and so now in the year of 2000, that means, well, how many years past 1960 here? That means it's right at that instance of being 40 years past 1960. Okay, so now I've spent also a good significant amount of time throughout the general lecture talking about what instantaneous rate of change means in terms of our work here in calculus. We're specifically looking at the derivative. And so now the only key to get to the instantaneous rate of change out of any function, we find the derivative. So now in your experience up to this point, taking the derivative of this function, I prime of t is a simple work for anyone at this point viewing this video lecture. And so needless to say, the viewers to this video lesson here can only understand this after you have mastered a certain level of, and at least understand my lecture in terms of what a derivative is. Okay, so now I prime of t, the derivative of our I of t function, now is going to be 6.29 times 2, because the power rule comes down, so all that's here, that's making it okay, so 12. 0.59 t. Okay, the power rule simply kicked in, the power went down and multiplied with 6.29 in front, and this should have been 58 instead of 59. Okay, and then minus 51.7. So this is our derivative value, and this general derivative function right here helps us find out the instantaneous rate of change at any instance. So now I'm about to, so that instantaneous rate of change at t equals 40. To find that, I am about to do I prime at 40. That's what it is. Okay, and that's how I'm going to obtain that. And so that means we're looking at 12.58 multiplied with 40. Okay, according to the setup of our general derivative of I right here, and minus 51.7. All right, so now I am quickly gonna swing by my calculator and do some quick calculation. All right, so my final answer came out, allowed me to write in this small, narrow little space here, but my calculation came out being 451.5. And same meaning. This value means it's in billions, the value we're measuring. We're still looking at the same function, I of t, so the outputs for that and the output amount is going to be already in billions. So this is, we're talking about a positive 451.5 billions. Okay, so as far as just getting the answer, that's the answer. We're done with that. But now again, I am going to quickly spend some time erasing the other board and then use that empty space there to make some interpretation, because really business field and economic studies is a good place that has a rich amount of application. So I never hesitate to explain as much as I can in terms of how these concepts in math we learn just straightforward as a math problem in the previous lecture, but now it has so much application. So what it says now is that exactly, or how about, that's not a good way of saying that, at exactly, okay, at exactly 40 years, okay, at exactly 40 years after 1960. That's precisely how we can say that, okay. So that's indicating it's only one single instance, okay, all right. And so at exactly 40 years after 1960, U.S. total personal income. And again, looking back at that answer, I have put in a box right here, it was a positive value, okay? And so now it's a rate of change. The meaning is a rate of change. So that means this quantity, our I value grew, again, it was growing. So at that instance, okay, and now I have to say that the U.S. total personal income was growing, okay, was growing, or formally increasing. All right, and now, so, and at this rate right here, at 451.5 451.5 billions. Okay. Dollars, of course. This is per year. I mean, I should have also mentioned in the interpretation of the answer in part A, it was also meant to be per year, but you know, I figure I just discussed, you know, in that 10 years it grew on average that whatever amount that was. So just forgive me that I forgot using that term per year. But that's the idea. Rate is always per year. And so now when we're talking about instantaneous rate of change here, using the word per year might make people think that, hey, but it's for 1 year long. But the point now is that this rate only happens at that instance where it's exactly 40 years after 1960. But then, surprisingly, I mean, in a real precise calculation, only half a year later, it's not going to be the same. It was not going to be the same rate. Okay? And so that's the idea right there. And that's how we can, that's how we're done and found the answer for this particular example right there, which has two different kinds of rates being asked for in this problem right there. Okay? And one of them, and of course, the instantaneous rate of change is ideally always the best one out there, because really when you are a lot more mature and become more and more professional in your field, in your business field here, in this particular example, I'm communicating with people who are intending for business field and economic studies, then the kind of applications you are dealing with out there will a lot of time involve functions that are up and down, involving a lot of up and downs in your functions. And so instantaneous, being able to obtain an instantaneous rate of change is ideally the best work with that, because that gets you the exact rate of change at an instance. And then in a different instance, you can apply the formula. I mean, you can apply the derivative work again and find a different instantaneous rate of change there. Okay? And that's for this particular example.